This episode is brought to you by Brilliant. In response to new quantum theories, Einstein quipped, "God does not play dice." One wonders what he would have said if he knew some of those dice are also highly explosive. Antimatter is the most destructive material in existence, to regular matter anyway. A gram of antimatter coming into contact with a gram of matter would destroy both, releasing 50 million kilowatt hours of energy. If done suddenly, it would explode with almost 3 times the power of the Hiroshima bomb, and if we can figure out how to mass produce and store the material, it could serve as both the greatest weapon and greatest starship fuel. But we can also use it for more peaceful, mundane, and smaller applications, which we'll be discussing today. When it comes to antimatter, we've got 5 areas we need to discuss. The first is what it is and what it is not. The second is how we could mass produce it. The third is how we could store it for long periods. The fourth is how we could keep this dangerous material secure from accident, theft, and sabotage. And the fifth is all its applications and uses as an amazing form of stored energy and initiator of desirable nuclear reactions. This is going to be one of our longer episodes, and we'll be dipping into particle physics fairly deeply, so now is a great time to grab a drink and a snack to power your brain. Antimatter, also known as mirror matter, is a material that's prone to a lot of misconceptions and confused discussion in both science fiction and popular science, and we need to clear some of that up. First, while antimatter in bulk form is quite rare, it is something you encounter all the time. Indeed, you have particles of it kicking around your body, though only briefly, so getting hit by one antiparticle will not make you explode. You've probably heard that bananas are mildly radioactive, and this is true. In rare cases, this represents antimatter in action. Potassium-40 is an isotope with a half-life of around 1 billion years, and one of its decay modes results in the creation and emission of a positron, the antiparticle of the electron, and this is an example of beta decay and beta radiation, terms which apply to both the emission of electrons and the emission of antimatter positrons. Beta decay happens every time any atomic nucleus decays in a way that changes the electric charge of the nucleus. This positron emission should not be confused with the atom containing a positron. It does not. This makes it totally different than an antimatter atom, which has shells of positrons around a nucleus composed of antiprotons and antineutrons. In the case of the simplest anti-atom, antihydrogen, there are no antineutrons. This gets at a key notion. Every particle type with an electric charge has an opposite version with the reverse charge. For complex reasons, our universe ended up with vastly more protons, neutrons, and electrons than antiprotons, antineutrons, and anti-electrons, or positrons. We're not precisely sure why, and it's quite possible there are universes where the exact opposite happened, so that protons and electrons are rare instead. As such, anti-universes would be identical to ours in their behavior, except all the people in them would be evil and have goatees, in accordance with the law of conservation of evil. Now, antimatter is not just reverse charge, it's specifically a particle of the same mass but with opposite electric charge, which is like static electricity, not flowing charge like electric current. There's more than just electric charge too, there's also opposite parity, meaning chirality, or in everyday terms which way the thread of the screw goes, clockwise or counterclockwise. At a deeper level, there are differences which help define the various particle families, such as color charge, with antimatter having anti-colors. Don't worry if you're unfamiliar with many of these terms, just know that they are aspects of subatomic particles which make for many unique kinds and characteristics. They can combine in many ways, as dictated by those characteristics. Where they can't combine, it is like oil not mixing with water, they just behave in their own ways. All these unfamiliar traits might just as well have been described in other ways, like shapes, sounds, or textures. In this context, color is the accepted term for the properties of quarks, which combine sets of 3 to form protons, neutrons, and their other class members. Quark color has nothing to do with visible color. We just found a property of quarks that came in 3 types, each with a reverse, and they got labeled as red, green, and blue to make visualizing them easier. They also come in anti-red, anti-green, and anti-blue, though we'll often use cyan, magenta, and yellow for them respectively. Again, nothing to do with actual colors. We just need a term for something we had no intuitive concept for. In truth, electric charge is made up too. Ignoring that all words are made up, some terms for electricity derive from terms used in artillery and cannons, where a charge is the gunpowder you put in a cannon. We also have the oddly named Quark Flavors, with up and down, the most common quarks, along with strange, charm, top, and bottom, and these have nothing to do with actual flavor or personality traits. It's common to say that when you combine antimatter with regular matter it explodes, but that's not quite true. A photon, for instance, has an antiphoton, but it is effectively just another photon, because photons don't have any electric or color charge, and when the two are in the same place at the same instant, they obviously don't explode. Indeed, a positron and electron don't exactly explode either. They are pulled together by their opposite charge and combine briefly. Then their tiny mass turns into a pair of energetic photons, gamma rays, which shoot off in opposite directions. This leads to one of the easiest ways to discuss the very tiny mass of the electron and other particles, using electron volts. When you collide a positron and electron, you get two photons whose total energy is equal to the mass energy of those two particles, and you measure that using Einstein's E equals mc squared. And now you know the mass, 511,000 electron volts each, or 0.511 MeV, mega electron volts per electron. Twice that for an electron-positron pair, either created or destroyed. 1 electron volt, eV, is the energy which an electron or positron gains or loses when passing between electrodes with a voltage difference of 1 volt. This is why you so often hear particle mass and energy given in electron volts, kilo, mega, giga, or tera electron volts. Everything was initially measured in terms of how an electron acted in an electric field of a certain voltage, and the nomenclature stuck for both mass and energy of tiny particles. Anyway, the explosive property of antimatter has to do with what happens when two particles of different net properties merge and give out new particles, usually some high-energy photons and often other particles that may be unstable. These properties are carried by leptons, a type of particle that includes things like electrons, positrons, and muons, and by quarks, the constituents of neutrons, protons, and mesons. So even though an anti-neutron has no electric charge, it is a distinct object that will annihilate if it closely encounters a regular neutron, or indeed a regular proton, but there's no opposite electric charge sucking the two together, so the interaction chance, often referred to as a cross-section in barns, is quite low. The neutron, unlike the photon and some other particles, is not its own antiparticle. Except in a perfect vacuum, collisions between free antiparticles and normal particles is not a question of if, but when. Also, it's an example where the annihilation product isn't just photons. You can get pions and kaons and gluons and other things too. Pions incidentally are two quark particles, so is the kaon, but one of those quarks is a strange quark rather than an up or down. And gluons bind quarks together, like electrons bind molecules together. In general, such two quark particles are very short-lived, and where quark-based annihilations are concerned, it's the quarks that are hitting antiquarks. It's not really about if they're a proton or a neutron. It's really if two particles are interacting, and if they just happen to be totally opposite, you get a pure annihilation and new stuff forming from all of it, be it photons, pions, or other particles, with photons being more easily absorbed. Normally stuff collides and interacts and most of the energy is just transmuting into new particles that all act very locally, while photons will generally escape that atom. Whenever we talk about nuclear fission or fusion and comment about how you're only getting 1% or less of the mass energy out of the deal, that's basically why. Virtually all the interactions that produce them is basically just shuffling around the particle types inside, with a little energy released externally. But when it shuffles all that into photons, that's a 100% conversion into a type of energy that can both escape the atom and be absorbed by other matter it runs into, like you. Neutrinos incidentally do have an antiparticle, the antineutrino, but neutrinos interact with virtually nothing, so it's not explosive the way we normally think of as antimatter. Getting whacked by hordes of neutrinos or antineutrinos isn't going to incinerate you, and a good thing too. We are all constantly penetrated by passing neutrinos, mostly from the sun, but only in the rarest cases is there any change to us from that passing swarm. We also should note that things like protons and neutrons aren't really made up of just 3 quarks. If you've ever seen quark mass and compared it to a proton or neutron mass, you notice that those up and down quarks only mass about 2.2 or 4.7 MeV each, about 4 and 9 times an electron or positron's mass, whereas a proton or neutron is around 2,000 times the electron's mass, the neutron being a bit heavier because it has 1 up and 2 down quarks instead of 2 up and 1 down, a tiny mass difference. Only around 1% of their apparent mass is actually the mass of those quarks. The other energy is in gluons, and we also have C-quarks, which are the virtual particles popping in and out of existence inside the nucleus all the time, the normal 3 quarks being known as valence quarks. That notion of stuff popping in and out of existence is worth keeping in mind, because it's a critical aspect of producing antimatter, since matter is popping in and out of existence all the time as virtual particles, and it always does so as a pair, a particle and its antiparticle. They generally annihilate near instantly, but by separating them we can produce and collect antimatter. I know this idea of seething stuff going in and out of existence tends to bug people, but this is mostly a product of trying to view quantum entities as stable classic objects with a macroscopic analog. Subatomic particles aren't little balls. They are stable or not so stable energy packets smeared across a place, and only certain combinations are stable. At super tiny timescales, many more particles and paired particles can exist. Without virtual particles, many important aspects of our universe would not function at all, fusion inside stars being a prime example. Stellar fusion cannot proceed until some protons change into neutrons, but protons cannot change into neutrons except with the aid of very heavy W bosons, which are more massive than entire iron atoms, and therefore cannot be treated as real particles in the not super high energy conditions inside normal stars. But as virtual particles, W bosons can be called into existence there very, very briefly. Quantum entities aren't objects but more like patterns of energy, and only a handful of patterns don't collapse. And there's always the mirror image patterns that are equally viable, the antiparticles. When those two meet, they collapse and that energy forms something else, but that something is always popping out with its own mirror image. Photons just happen to be their own mirror image. Related to these virtual particles is a virtual energy to space-time. A little handful of space has some energy in it, in addition to all the atoms or photons actually passing through it, and that base level of energy is constantly seething around, forming a pattern and its anti-pattern, and pretty much falling right into each other to recombine and vanish. As these were virtual patterns, they leave no residue of real energy. Every so often, stable matter or energy will bump through one of those virtual interactions, and something else will happen as that particle interacts with one of them, and that's essentially how all the various subatomic processes happen. But if you had a virtual electron-positron pop inside a very strong electric field, and this has to be very strong because they're really close and opposites attract, you could pull them apart and make new matter. This is not free energy though. You have to provide real energy in order to make the virtual pair become real. On their own, those base level energy fluctuations of space-time always return to the zero level, hence all the talk of quantum fluctuations and the vacuum not really being a vacuum, but bubbling and seething with potential or vacuum energy. It really is often easier, and reasonably accurate, just to think of it as a big soup of energy out of which some more packets of energy can sometimes linger as what we think of as particles for long times, which in particle terms can be anything from a trillionth of a second to trillions and trillions of years. Some energy configurations are more stable than others, those we call particles, but the vast majority aren't stable at all. Anyway, this is not a particle physics lecture, but we had to go over some of that to explain why it's so hard to make and store antimatter, and why it's so useful if we can. Which is to say, it is stupidly easy to make antimatter, but it's really hard to do it in a way that lets you grab those particles before they ram into something else and go away, which is a big issue for production and storage. Virtually all matter, at the molecular and macroscopic scale, is electrically neutral or very close to it. If you try to cram protons or electrons, or their antiparticles, into a box with just one type in it, the amount of electric force they have would be massive. Electromagnetism is trillions of times stronger than gravity, so you can't make a box full of protons or a box full of electrons, because the repulsive force between them all is insane. Similarly, you can't make a beam of electrons or protons stay together, because they're trying to shove off each other into a widening cone. And if you're mass-producing antiparticles in some spot, they're all trying to shove off each other and scattering and running into things that will blow them up. You need to produce them as charged particles in order to separate the matter and antimatter particles, because they actively seek each other out if mixed together, but you need them to be mostly electrically neutral if you want to store them at some useful density. Not totally neutral though, so that you can actually move the stuff around electrically or magnetically. We might have one possible mode of production and manipulation suggested, like the Stelaser, by the fertile mind of Steve Nixon, a method that's still a bit out there but maybe could be made to work. You've heard of using lasers as optical tweezers, I'd imagine, and they'd be one way to manipulate these particles without electrostatics or magnetostatics, allowing us to play with electrically neutral antimatter. Since these things we call particles can be thought of as really being energy patterns with specific wave states, we might be able to literally build them out of light, in the configuration and location of our choosing, using certain extensions of 3D holography, essentially using a specialized waveguide to produce two equal and opposite interference patterns of intense light to pull the desired particle pair out of the quantum foam and tease them apart. Be it an electron and positron, or a proton and antiproton, or a neutron and antineutron. Eventually even something much bigger like a molecule and its anti-molecule, which would be a lot easier to store at a desirable density. That's pretty far out there and probably a topic worthy of its own episode, but deserves a mention, particularly since your ideal antimatter for storage is something bigger and more stable than a gas of antihydrogen. Normally we talk about creating antihydrogen by just getting an antiproton and positron to link up, but we'd infinitely prefer big macroscopic slabs or beads of some material like anti-ion, which you could easily store by old-fashioned magnetic levitation in a small vacuum compartment of some material that's not getting wrecked by a very occasional single atom annihilation, essentially a normal bit of radiation shielding material. There is a type of titanium we believe is produced by white dwarf collisions and their resulting supernovas called titanium-44, which is highly radioactive and decays only by electron capture, then goes on to produce antimatter positrons. We see its telltale antimatter annihilation, gamma-ray signature near our crowded galactic core, but it is produced throughout the galaxy. Titanium-44 has a half-life of 60 years, but it is believed that its half-life increases with ionization and becomes stable when fully ionized. It might not be antimatter itself, but may allow us to safely and more easily use its positron-antimatter decay product in our matter world. Eventually we may send harvesters to collect Titanium-44 from white dwarf supernovae, or learn to produce it efficiently locally. Now on the production end, in the more near-term and tested fashion, you've probably heard we need to dump many millions of times more energy in to get antimatter out. We have been getting better at that, and it's worth noting we don't normally set up particle accelerators with mass production of antimatter in mind. They are normally just particle experiments to find and measure exotic particles, not mass produce them. We've had design concepts for mass production for decades that were thought to be able to do more like 10,000 to 1, which sounds terribly inefficient but surprisingly would be very useful. Back in 1995, in his book Indistinguishable from Magic, Robert L. Forward suggested using a large solar array about 100 kilometers across with a power output of about 10 terawatts to produce about a gram of antimatter a day. Again, that's inefficient as heck, but we've talked before about possibly shading the Earth to cool it, and such a panel would help with that. Or to switch over to using power satellites to beam energy down to Earth. And since you always want more output capacity than you need, and solar panels have no fuel they burn, you could use the surplus capacity or excess outside peak hours and days to run such antimatter factories. Similarly, we've talked about the simplest of Dyson spheres, swarms of thin mirror power satellites, statites or lagites englobing the sun, which could be constructed using relatively little mass, exactly the sort of manufacturing a simple and early designed clanking self-replicating machine would excel at. Something like that built by such machines could probably be assembled over a vastly shorter time span than it would take for human populations to reach the number needed to fill out a Dyson swarm of habitats. Folks often ask what you do with all that power. Producing antimatter that way, even at 10,000 to 1 efficiency, is one example of what you could do, producing a few million tons of antimatter a day. After all, minus the ecliptic plane the planets are on, we don't use any of that sunlight and it just goes to waste in the void. so we might as well get use out of it even if it's inefficient use. 1% of 1% is far better than 0, especially when talking about starting with 2 billion times more energy than received by the entire Earth. It is worth noting though that there are some natural sources of antimatter. Cosmic rays tend to produce it, and we estimate about a kilogram of antiprotons passes through our solar system every second. We could potentially scoop it up from the upper atmospheres of any of the planets, and the gas giants have a lot more than we are producing now. Saturn has about 250 micrograms produced each year. Still, that won't get the job done for anything but scientific uses, or for sending off tiny probes. Though if those tiny probes are von Neumann probes, self-replicators that can arrive at another star after making the journey at a high fraction of light speed, and unpack and build stuff, like the interstellar laser highway system we've discussed using before to let ships run on rivers of light between stars, that's another thing you can use the sun's excess power for. Our local natural sources just can't be regarded as anything more than meager, but it is worth noting that things like black holes and neutron stars can spew antimatter out. They are essentially giant high-powered particle colliders with relativistic particle jets, so those might become antimatter farms in a distant future. And I say farm rather than mine because you could augment the process around them to fertilize production and harvest antimatter. In many cases, antimatter production might simply be a byproduct of another process too. We talked about using surplus, space-based solar power to run production a moment ago, but you might get antimatter as a byproduct of power production too. Short of farming it in an extreme astrophysical setting, it's not very likely anyone would ever come up with a way to economically power a civilization on antimatter, as even a high-efficiency method would still need more power input than the antimatter produced would release. But we have a concept called antimatter catalyzed fusion. Same as we can catalyze fusion in a hydrogen bomb using a regular fission bomb to set it off, itself usually set off by conventional chemical explosives, you can catalyze fusion by using a tiny amount of antimatter. Current estimates say you need about a microgram of antimatter to trigger a thermonuclear detonation, and it need not be a big one, making it ideal for things like post-nuclear spaceships, as we looked at in the episode The Nuclear Option. Ideally, we'd like a spaceship that used pure matter-antimatter reactions for fuel, but fusion-driven ships are nothing to sneeze at, and antimatter-catalyzed fusion might be a good way to do this. You could also potentially be using the power produced by the fusion event, which is much more than that released by the antimatter catalyst, to power more antimatter production. Producing your antimatter for this process while you're in flight would be very handy, given the storage issues with antimatter which have been mentioned. We'll get back to them in a moment. First though, there is an alternative version of catalyzed fusion using muons rather than positrons, antiprotons or antineutrons. Muons are short-lived and much more massive versions of electrons, often generated in our atmosphere by cosmic ray proton collisions that first yield pions, which then decay into muons. You get hit by thousands every minute, and they've got a good penetration value. They can bounce around a lot, and this can be used to catalyze fusion in deuterium or deuterium and tritium. This is an amazing way to catalyze fusion, and to do it at room temperature too. And this one isn't theoretical, it's been done in labs plenty of times for decades now. It also produces antimatter as a small but significant byproduct while it's at it. However, it's got a couple problems. First, the muon will stick to an atom a bit less than 1% of the time it hits one, so it only bounces around so many times, igniting fusion events before it decays. And second, we're quite inefficient at producing muons, much like antimatter. If we were better at producing muons efficiently, that alone might solve the problem, but it is possible we could set this up on a grander scale in some environments that were more hospitable to this process, such as the atmospheres of gas giants. Again, as suggested by Steve Nixon, here are some methods of defeating the problem with getting power from muon-catalyzed fusion. Getting some fusion energy is easy, but getting useful net energy is not. First of all, the deuterium and/or tritium needs to be in a very dense form, so that many useful muon collisions will occur during the brief lifetime of each muon. That either means insanely high pressure, use of liquid isotopes of hydrogen, or both. The usual method has been bombarding cryogenic liquid deuterium with muons, and it works very well for warming the supercooled liquid, but that only consumes power for turning the gas back to liquid. The problem is the liquid is made at a much colder temperature than the ambient temperature anywhere on Earth. That kind of refrigeration consumes a lot of energy. To turn this fusion into an energy source, the dense state must be achieved cheaply, and the warmed state must do net work, just like the Rankine cycle using water and steam in a normal steam electric generating station. Normally, like with any other gas, compressing hydrogen isotopes to high pressure as gases uses a lot of energy and generates a lot of waste heat, so that is not a productive path. But if a very cold heatsink was available, like the middle to upper atmosphere of Neptune, then the gas could be compressed and even liquefied using a relatively small amount of energy. Gas giants also contain vast amounts of deuterium. It can be separated from the other gases by any of several methods before, during, or after compression and liquefaction. By pumping the liquid deuterium up to fairly high pressure, which uses little energy since liquids are essentially incompressible, then injecting negative muons into it, the liquid will warm and partially boil at that high pressure. Then it can do work in a turbine generating power. The slightly warm gas exiting the turbine will now contain a little helium, which can be removed in various ways, while the deuterium fraction is recycled, cooled, and compressed again. That leaves the problem of making the muons, and some antiprotons would be nice. We could export those. Antimatter is definitely worth the cost of hauling out of deep gravity wells. Some deuterium may also be exported. To make antiprotons, accelerate protons, atoms of normal hydrogen, to about 50 billion electron volts. Then smash those together with similar protons going the opposite direction around the accelerator. Result, a few proton-antiproton pairs, a lot of pions since they are the lightest mesons, and some energetic photons. The pions decay very quickly into muons, from which the negative muons are selected and sent into the fusion area. The energetic photons from all that can be used to reheat the warm deuterium after some in-turbine expansion, and/or used to further heat the high-pressure deuterium before the turbine. Waste heat from this heat engine is still rather warm compared to the atmosphere outside, so that heat plus waste heat from most of the other areas of this antiproton factory is transferred into one or more balloons filled with the light hydrogen gas. That provides the lifting force to hold the entire antiproton factory at the desired altitude in the sky of the gas giant. You then accumulate antiprotons until there are enough to make a shipment, then launch them into space, perhaps on a rocket using antiproton catalyzed fusion of deuterium. An extremely large number of these antiproton factories can operate all at once in the skies of mini gas giants. Total production rate of antiprotons can be made rather high, plus deuterium and even some helium-3 can be exported. Otherwise, those gases will sit there in those gas giants for billions or trillions of years, doing no good for anybody. I said a bit ago that it would be nice if you could produce your antimatter while in motion on a spaceship, and that brings us to the storage issue. We have a device called a penning trap that is basically just a magnetic field, usually inside a cylindrical body, that can keep particles with an electric charge confined within it instead of hitting the sides. Now, the best we can do at the moment with these is to keep stuff confined for about half an hour before the particle just happens to get on a trajectory that isn't confined enough and hits the side, but that can be dealt with by size and temperature. Antimatter we make now is very hot. It has a ton of kinetic energy when made by the processes we use, ultra-relativistic collisions, and such bottles aren't big, which means it bounced around a ton of times in a short period. Double the size of the vessel and you double the lifespan of the stuff inside it, since it has to cover more distance between bounces and interactions. Lower the temperature and you achieve similar. Cooling antimatter is rather tricky since at that scale cooling is achieved by slowing the particle down, which is usually via collisions with other stuff moving slower. But you could do this via an electric field or optical molasses, and also produce your antimatter at lower energies. As I mentioned before, we don't really make the stuff with mass production in mind, and your typical super collider operates at particle temperatures far beyond the inside of any star's core. This is an example where scale helps, and while antimatter's portability is a big part of its value, so that we wouldn't want giant penning traps, it's perfectly fine to have an antimatter factory with hundreds of kilometers of length to be used to slow down or cool antimatter, to be transferred into something smaller once that's done. The same is the case for trying to build large chunks of antimatter, as pellets of something like anti-carbon or anti-ion or whichever, that just had enough ionization to let you hoard the pellet in magnetic levitation in a vacuum flask. Your default ideal storage device would be one with an equal mass as the antimatter within, since that becomes a self-contained device. Antimatter by itself produces no energy, any more than regular matter does, what does the job is antimatter and an equal amount of matter, with both being converted into energy, and to get a gram of the stuff is equivalent to a 43 kiloton atomic warhead, since 2 grams are destroyed. And if it's a weapon, you don't have to worry about a source of matter because that's provided by the target it strikes. Your typical bullet has a mass of 20 to 40 grams, though varying widely on caliber, which means a bullet of antimatter can produce an explosion big enough that only someone using a very long-range rifle wouldn't be in the blast zone of their own weapon. You could obviously do much smaller bullets or ones with less antimatter in them, and if you're good at manipulating and storing the stuff, it also gives you an alternative to chemical-powered firearms. While electromagnetic railguns are a popular idea, getting those compact and high-powered enough to be man-portable is no easy thing, whereas antimatter is as superior a substitute for gunpowder as it is for rocket fuel, and would allow you to fire shots at very high speed, only limited by friction in the air, and up in space allows weapons to move at relativistic speeds as an alternative to laser and particle beam weaponry. Needless to say, it lets you pack quite a warhead into the shot too. Which raises the physical security issue. Now, while I and others have raised the concern that a society might collapse simply from having technologies so dangerous and easy to produce that any lone lunatic could manufacture a doomsday device in their basement, and while antimatter is a common example, in practice it's very unlikely it would be. You would not mass produce antimatter on planets in all likelihood for the inefficiency and waste heat reasons we outlined earlier, but it's also a power glutton, and that makes it easy to detect if someone is making it on a planet. At best, you're producing it by using the same amount of energy as it will eventually produce, and in all probability even the most efficient process is going to be an order of magnitude less than whatever fuel and power system you're using to make it. It is not free energy, and some would-be terrorist is going to be given away by the giant electric bill and huge thermal blossom at their facility. You're going to notice someone using 10 times the normal electric consumption they should be, and if that were the regular American household, that roughly 40 billion joules they normally use a year is only going to net them the equivalent of 10 tons of TNT. Nothing to laugh at, but they'd need thousands of years at that rate to get it up to atomic bomb levels of explosives. You probably could get away with producing it a couple orders of magnitude faster, and you don't need a gram of antimatter to wreak nuclear havoc. We talk about suitcase nuclear bombs, but the antimatter equivalent is a pen-sized bomb or even a pinhead nuke, just depending on how small your penning trap or alternative storage method is. And let's not forget, it can be used as a fusion catalyst. If a milligram of antimatter is suddenly injected into 1 liter of liquid deuterium, the results may be very like a nuke, but with no need for fissionables or even high explosives to kick off the bang. Now, that said, you'd almost have to smuggle something like that in from off-world for anything in the kiloton or higher explosive range, unless a very big group or country was involved to obscure your power usage or let you siphon from their own stores. And antimatter is the sort of thing you'd store in quantities as small as you could, for fear of accidents, and as large as you needed to ensure efficient and solid security on it, while being economical with your security assets. I don't think you'd store it on planet in quantities big enough to go off as a nuke, when you could distribute it to more the scale we'd associate to a modern fuel depot going up in an explosion. That smuggling issue is not quite as bad as the tiny size implies. First, a pen is not a small thing in terms of people or cargo going through ports of entry, and if we're talking spaceports you process through before you go down to Earth, then we're probably talking pretty high-tech scanning. I don't think you could hide even a small hollow and magnetic cavity that was storing more than a milligram or even micrograms just from the kinds of scanners we can make now, especially if those are being run by fairly decent AI analyzing the scans such as we're starting to employ in a lot of medical scanning. A milligram isn't anything to sneeze at either, but it's no worse than a large truck bomb, at least as a pure antimatter bomb. The fusion catalyst option is worse. Speaking of those scanners though, one example is an MRI, a magnetic resonance imaging device, keyword there being magnetic. Penning traps or other magnetic confinement systems rely on very carefully keeping antimatter magnetically penned up, and disrupting the magnetic field is going to have explosive results. It's also a defense against antimatter weaponry, like torpedoes launched by spaceships or orbital platforms, since they could hit the incoming devices with magnetic bursts as an alternative to shooting them down. You proof such devices against that by either employing magnetic shielding or keeping the antimatter inside very, very cold so that the particles inside aren't bouncing around fast, and it will take a little time to go off, and you counter that for hidden bombs with quarantine periods. We also don't have any materials that are much good at shielding from magnetic fields, and those all rely on thickness. So borrowing some advanced metamaterial that let you shield very strongly against magnetic fields, and with a very thin layer of shielding, you're going to be able to detonate hidden bombs with your scanner. Of course, we might get those magnetic metamaterials in the not too distant future. See our metamaterials episode for more discussion of that, which might be problematic, but on the bright side might also be useful for storing or making antimatter too, amongst many other great applications. We also don't want to think only in modern terms when it comes to detection. It's entirely possible the customs and border security in the future will be a trillion tiny little robots that go into someone looking around up close and personal, scanning for dangerous viruses, mysterious microscopic cavities in bones with high explosives or equipment in them, and so on. Of course, if they find it, that person might detonate themselves, as would occur with a magnetic scan. Now, losing a spaceport or city security outpost to such a bomb is no laughing matter, but you could do small and isolated ones and potentially even telepresence for the folks manning them, so they were far enough away from the worksite while scanning people. Also, antimatter is not infinitely powerful. Even an entire kilogram of the stuff going off inside a tiny space station in high orbit is only going to get a fairly tiny amount of your planetary orbital swarm, and the real danger there would be setting off a Kessler syndrome event. See orbital infrastructure for more discussion of that. We also might be able to get around some of the accidental explosions by not employing normal matter. I suggested big slabs of anti-materials like anti-ion earlier, because it's less of a containment problem than anti-hydrogen gas if you can make it. But every particle has antiparticles, and that includes things not made out of up and down quarks, like strange or charmed matter. You might make stable atoms with those types of quarks in them, and others with their antiparticles, and use them as your antimatter power source, since they can only annihilate with each other, and strange and charmed quarks aren't exactly hanging around our solar system in abundance. Needless to say, once we can start producing more of it and turning our minds to dealing with it, we may come up with all sorts of other safety mechanisms for storage. So it's quite a security issue, but not a boogeyman, and probably rather manageable, like most security issues arising from new technology. It's very useful stuff too, so as you get better at producing and storing it, you figure out what level of usage is safe from accident or malign intent and employ that. Obviously, the big use besides weapons is spaceship fuel, because it's compact in so many ways. There is no better rocket fuel than antimatter. It outperforms even Hawking radiation drives on micro black holes, and is easier to make small ships out of. The only rival would be light stored in a box that was a perfect mirror, since that's also a mass energy level device and is essentially what antimatter is doing. You don't need any high-tech spaceship to get near light speed if antimatter is your fuel, and it's also an amazing fuel at any other speed too. There's no complexity in its actual use, just the making and handling parts. You combine it with matter and you get a ton of energy. But we don't always need a ton of energy, and that's where it has some novel applications. Given the security risks, it sounds absurd to have cars or appliances powered by antimatter, but keep in mind that it's all about quantity. Tiny machines with microscopic penny traps, or even nanoscopic ones, may be an ideal compact power source for very long periods, at least for lower energy antimatter like positrons. Keeping in mind that antimatter is about 1 billion times more energy dense than the typical chemical fuel, and even more so than our best modern batteries, and probably can be made tinier than a gas engine. If we were using some exotic matter like strange quarks, we might not even have to worry about an explosion if the containment got ruptured. And again, if you're substituting for a normal modern fuel, there's no more energy there than the fuel already contains if it ruptures its tank and goes boom. Indeed, rather less, since you need to pay extra energy to tote your fuel and associated equipment around, which is a very big deal for things moving fast like airplanes and especially like spaceships. That is definitely a long way off, and quite probably never, but I really wouldn't be too surprised if a time machine to the 23rd century saw folks walking around with tiny bits of antimatter running their ultra-smart phone or personal cybernetics. That explosion issue is also less important for military application than regular folks walking around on their regular daily business, so we might see forced use in things like military vehicles, armored exoskeletons, giant mecha or war robots, or power armor. In the short term though, antimatter technology is already in use. Beta decay atomic batteries may see regular usage in coming decades, and its medical applications are already there. I mentioned MRI scans earlier, but we also have PET scans, and that is short for positron emission tomography, antimatter already being used to save lives, and we've been experimenting with using antiprotons for cancer treatments too. Back in the early days of sci-fi, we often heard folks saying we were entering the nuclear age, but antimatter is far more powerful than fission or fusion, so it might be that the future isn't nuclear, but antimatter. Dangerous stuff, but if you don't anti-mind, it doesn't antimatter. So we covered a lot of particle physics today, and it can be a confusing topic considering how counterintuitive quantum mechanics often feels. If you'd like to learn more about quantum mechanics, then I'd recommend Brilliant. Brilliant has an excellent online course on quantum objects that will walk you through not just the basics of quantum, but even fairly advanced concepts, and do so in an interactive fashion. In a time when more folks are embracing online education, Brilliant's focus on fun and interactive methods makes them a great choice, whether you're a student, a parent trying to enhance your kid's education, a professional brushing up on cutting-edge topics, or someone who just wants to use this time to understand the world better. You should check out Brilliant. Try adding some learning structure to your day by setting a goal to improve yourself, and then work at that goal just a little bit every day. Brilliant makes that possible with interactive explorations and a mobile app that you can take with you wherever you are. If you are naturally curious, want to build your problem-solving skills, or need to develop confidence in your analytical abilities, then get Brilliant Premium to learn something new. Brilliant's thought-provoking math, science, and computer science content helps guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with your interactive explorations. Over time, you'll be amazed at what you can accomplish. If you'd like to learn more science, math, and computer science, and want to do it at your own pace and from the comfort of your own home, go to brilliant.org/IsaacArthur and try it out for free. So next week we'll be returning to the Alien Civilization series to consider the notion of aliens who come in peace, and actually mean it, in Benevolent Aliens. Then we'll close out the month of May with our monthly livestream Q&A in our new SFIA studio on Sunday, May 31st. We'll then jump into June and summer by returning to Jupiter to contemplate the idea of making Jupiter into another sun, and look at some techniques for how we might do that and why we might want to in Summer on Jupiter. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you enjoyed this episode, hit the like button and share it with others. And if you'd like to support future episodes, you can support the show on Patreon or visit our website isaacarthur.net to donate to the channel, see our list of episodes or book recommendations, or buy some awesome SFIA merchandise. Until next time, thanks for watching and have a great week.